Okay, so firstly, for advice for the week, I believe that I've gotten through all of the TLC lab notebooks. If you haven't received a grade yet on your TLC or your melting point recrystallization lab notebooks, the first two experiments, please contact me. There may be a discrepancy there that we might need to clarify. I know this semester has been kind of tough, and I'm being more flexible with our starting deadlines, especially with the weather and everything that happened at the start of the semester, let alone this being a totally online class. So please contact me if there are any assignments that you missed and you need to make up, and we need to just get everyone on track. But starting from now and going forward, everything is going to be due in a timely fashion as it's going forward. So please, please, please reach out to me ASAP, like that big email that I sent out. If you have anything that's outstanding, let's take care of it as soon as possible, so that way that I can get you an on-time grade and we can all get through this together. So one note on lab notebooks, if you are writing it instead of creating it into Microsoft Word, make sure to write it in pen, so that way that it's more legible if you scan it. Like, don't use pencil. Make sure that it's black ink, just so that way when you scan it with Adobe Scan, it's the most legible. Additionally, if your handwriting is poor, make sure to focus on it. And if you can't write legible enough for me, then please just go ahead and use Microsoft Word, just because if I can't read it and it's not legible, then I'll have to reduce points, just because if it takes me a while and I have to strain my eyes in order to review your work, unfortunately, that will be reduced points, just because it's not an applicable use of my time or your time for me to be reviewing handwriting. Going forward with that, the main thing I noticed on the lab notebooks is that we'll want to make sure to list every hazard. And by that, I mean every single chemical that we'll be utilizing in the lab. So with this lab, when we review the lab manual, I'll go ahead and list out to you every chemical this run. But I expect going forward, make sure every single chemical is listed out in your hazard section. Secondly, oh yeah, go ahead and add their waste disposal. So it should be organic, aqueous, or solid. This would be more understandable if we were actually in the lab, because at that case, we would have the 3 bins where we'd be disposing of it, and then you would know from where you disposed of it within the class. Finally, the glassware, make sure it's in the apparatus section, and make sure that the size is listed, because there are multiple sizes of glassware. And in order for you to understand this experiment better, you need to know exactly the size of the glassware you'll be utilizing. Some of them are more uniform, like the condenser is a pretty uniform size. There are larger condensers, but that's usually not utilized in lab unless you were distilling like very, very large systems, like multiple grams or kilogram scale. So things like that, like just a condenser, that's cool with me. But like a beaker or Erlenmeyer flask, those can range from like 25 milliliter all the way up to liter size. So we just want to make sure, let's not miss out on the sizing. Make sure to list those out. Just review the lab manual and see exactly the sizing that they refer to within it. Then going forward, those are the main notes I had for the lab notebooks. I've been adding comments at the end after I grade your lab notebooks, so you can see what to do. And this week, I finally have gotten through a lot of like my quizzes and tests from the previous week, because everything was backed up. So I'm going to try by Friday to be getting everyone out the 3rd lab reports. Let me see what we had there. For our group, because we're group C, the 3rd lab report, we had safety, that was not much. The recrystallization melting points, that was completed. TLC and column, I'm pretty sure I finished everyone here. If not, let me know. There may be a discrepancy in uploading situation. That's another thing. If you have a quiz or your notebook, double, triple check when you upload something. Like, just go ahead and click it, and then you can pull it up and see exactly what you uploaded. Because I noticed that some people, and I can't remember if it was this section or the section before, that some people had uploaded either only the first part of question 5 for their polarimetry, I believe, or no, it was the simple distillation. Some people only uploaded part 1 of 2 for that question, and you need to upload both, or I can't give you the grade for it. So make sure that double check what you've uploaded, so that way that you know that you've uploaded every part of the entire question as the answer is given. It looks like y'all have been doing great so far on all of your uploads in terms of whenever you get it turned in correctly, but double check to make sure if you are missing, or if you're missing a grade and I said that I've already completed grading it, then go ahead and reach out to contact me towards that, because I've tried to individually contact people, but it's becoming more of a quantity situation now, in terms of trying to reach out to individuals with where they hadn't uploaded their certain objects that they needed, or PDFs that they needed to, for me to be able to grade it correctly. And let me see. Yeah, and I'm gonna try to give a little more detail as to the question and answer. I'll try and type out more of a descriptor for those specifically towards like which question and answer they'll be. And oh yeah, let me see. So, just so I can list out what exactly I've gotten through before I pull my screen up to go through our module today. Let me list out for you all section. So the lab notebook I've gotten through, or the safety lab notebook, that one was completed. If you are missing a grade there, then please reach out to me and we can see what we can do if you want to do it like late or something, because it's been a few months now. Experiment 1, melting point and recrystallization, it was completed. Please reach out to me if you intend on turning that one in. And the TLC is completed as well for the lab notebooks. So I need to work on the simple distillation. I need to grade y'all. The fractional distillation I need to grade. And then of course the polarimetry, since that was just turned in, that's not going to be completed. So I'll either do simple or fractional here this week and get it done before the weekend. And hopefully, as long as that my course load stays a little lighter this week, I possibly will be able to get out a second notebook. I don't want to give up, blank promises to y'all, and then you end up seeing there's only one lab notebook graded. So, okay, Oliver, yeah, I'll switch those two. I see what you said there. Okay. Yeah, and then the lab notebook should say the size. Otherwise, we can review the module and I'll kind of list them out to you. If it's slightly ambiguous and you list something and then you're like, I'm not sure, then I can send maybe a small email out to everyone just to say, hey, this is the size of this glassware, so that way we know exactly what everyone needs to use. I don't want people to just lose points over little things, but it is critical since we're just doing an online lab for everyone to understand the size of the glassware that we would be using. So the quizzes I have been pretty on about. I just need to clear out, it looks like I only need to clear out a couple of the fractional quizzes here. The rest of them are good. Mainly the notebooks I need to catch up on grading for y'all. So I will try, I'm definitely gonna get through either the simple fractional by the end of the week. And then additionally, I'd like to get through the simple or fractional, like, whichever one I don't grade. So hopefully if I work hard enough, I'll be able to get both of those graded and y'all can review them. It looks like everyone's basically understanding how to do them. So I think that we'll do fine with that. Just try your hardest to study for those quizzes so that way you get really good grades on that. And then just make sure to always triple check your notebook before you submit it, so that you don't lose little points from miscellaneous things within it. And let's see if I missed anything. Yeah, and always you can double check the video like Sarah was saying there, that they may mislabel things within the video as well. So you can always check that, and you can check the module. So let me go ahead and pull up this so I can show everyone. Let's see, share screen. So today, over here, here's our group C. If you go to module under Canvas, like we've done before, go to group C, and then you can see the schedules at the top that'll show, but you can see week by week where we've gone through so far. TLC, fractional was the week off that I posted a video. Simple was the week prior to last week. The polarimeter was last week, and then this week we're going to be doing the separation of organic compound by acid-base extraction. The one thing I did want to notice was the HOLA ChemX discussion and poster. Make sure, if you haven't done it yet, to go into here and go ahead and complete the discussion down here. It's fairly quick, not too difficult. The primary thing is to complete this discussion sooner than later because Dr. Astogi keeps bringing it up every week and it looks like that we only have a few students who have completed it so far. Primarily, I would prefer that everyone complete the discussion as soon as possible so that you start getting it fresh in your mind before spring break. And if you can start on spring break, that'll be good for you as being proactive towards this because the poster is due May 1st by midnight. However, once April rolls around, you're going to get started for cramming for your last tests running around, your last quizzes, your finals. I really recommend just slowly start it up, maybe work on it an hour or two a week, or even 30 minutes. If you start putting in 30 minutes a week now, then you'll, by the time that May 1st hits, you'll be prepared instead of just waiting until the last week of April. And I'm just going to keep reaching this out to everybody to remind y'all that, hey, this is looming in the distance. We're in March now, March 9th. So that means we have 1 week, 2 weeks, 3 weeks, 4 weeks, 5 weeks, 6, 7, 8, 9 weeks of left until the project is due. So just keep your eye on the ball and make sure if you haven't started to go ahead and try and start it up, make an idea, get the discussion done ASAP because it's an easy, little quiz, if you will, to get through with and to make sure to start up on that poster. So yeah, here's my friendly reminder for the week. Let's go ahead and go back to modules. And we will be working this week on the separation of organic compounds by acid-base extraction. So one moment, let me move this. Firstly, as usual, we're going to be reviewing through the lab manual in order to comprehend the subject at hand that we're going to be reviewing today. Secondly, after this, go ahead and watch both of these videos. It's great to watch so that way you can visualize everything that I'm going to explain to you. And I'm going to utilize as much language that I can to explain to you. But again, it is very critical to watch these videos so you can see a hands-on demonstration because watching the video will allow you to see the acid-base extraction occur in real time, as it is a very critical technique in organic chemistry for people to use in a lab. And I use this almost every single week when I'm in the lab doing research. So hopefully you'll be able to utilize this if you ever go forward with either research, performing chemistry, or maybe you'll end up utilizing it in a future chemistry class. So yeah, make sure to watch these videos, secondly. Thirdly, we'll check the pre-lab notebooks on a few people here in a moment once we get through the rest of this module. Fourth, remember to complete your pre-lab quiz by the end of the week. Then here is our items for our lab day. So firstly, we have our graduated cylinder. It looks like here we would have a 50 milliliter one. And here's our separatory funnel. This would be a 125 milliliter one. Oh, and also remember, this will be posted on Zoom. So if, or on YouTube. So if I talk too fast, you can kind of just skip to this part right here where I'm reviewing it. And then you can write down every single one of these. And then we'll go forward with that. Here we have Erlenmeyer flasks. So these are larger. These are about 125 milliliter. Within my lab, we have even like super tiny ones that are like 25 milliliters and also a little bit bigger, 50 milliliters. So it's critical to understand the size of these because if you pull out something like a liter Erlenmeyer, it's kind of hard to pour out your solution. Maybe you'll have stuff stick to your glassware and lose some product along the process of research. So it's important to understand the sizing of your glassware. Thirdly, I believe here we have a 250 milliliter vacuum flask. I believe this is what it's called. I'll have to look it up here in a moment. And here's your Buchner funnel for you to be able to go ahead and perform your vacuum filtration. And let's see, here's your beaker. I would say that's about a 200 milliliter beaker. And 2 watch glasses. Don't worry about the size for watch glasses. There is like small, medium, and large of those. I'm not too worried about that. It's mainly the descriptor of understanding your sizes. If it's a 125 milliliter Erlenmeyer and you say that it's a 75 or something, within that range, that's cool. But if you just say that it's an Erlenmeyer, then I could throw something at you and be like, well, is it a liter or is it a 50 milliliter? Because those are like massive difference. So give a little, ballpark guesstimation. If you're a little wrong and you say like 125 instead of 100, I'm not going to take points off of that. I just want everyone to understand that the sizing is relevant to the quantity of scale that we're working on with this given experiment. Then you have your bulb here. and they're missing a pipette. There should be a glass pipette since you have your rubber bulb here. And finally, you have your spatula here in the middle. And so, yep, we are online like usual. After the lab, make sure to go forward and review this video if you need to in order to understand the lab manual a little better and complete your post-lab notebook. There are post-lab questions throughout this time. And let's see, and then the data. So we'll review the data after we go through our lab manual. So let me go back. And so I'm just going to type a few people's names out if you can show your pre-lab. So let's see. Okay. Okay, so please show your pre-lab. Let me go ahead and open up sharing. It's Michaela, Jennifer, Adriana, Pedro, and Jasmine. If you can just show me either the physical pre-lab that you have or, okay, great, Jasmine, thank you. Okay, Michaela's sharing her.
I can share my screen, but it's not letting me like close Zoom, so it's like hidden behind. So let me figure that out for a second.
Yeah, no problem. Okay, I'm just looking at Michaela's. Okay, yeah, so scroll down. Great, okay, good.
Also,
so yeah.
my grade in Canvas is locked. Like I don't.
Yeah, we were having something with that. I need to email. Dr. Rastogi hasn't responded to me yet, but yeah. So actually, scroll up. Let me show the people here really quick your hazards, just so that they can see. So here, hydrochloric acid, aqueous, that's good. Scroll up, 3-nitroaniline, organic, that's good. Make sure that you look up the difference between these, because if we were in lab, we need to make sure that we understand where to dispose of these chemicals properly, because if you put something that's organic and cannot dissolve in the aqueous waste, it would just sit at the top of the aqueous carboy is what it's called. It's a container that we dispose of all of our aqueous waste. So just always make sure to look up online what type of waste it is, so that way you know how to properly dispose of it if you were in lab. Okay, so yeah, Michaela, you're good. You can stop sharing. And
I can share whenever you're ready.
Yeah, Jennifer. So if you click share screen, it should allow you to click specifically onto your Word document. There you go. Great. You can just scroll down a little. Cool. Yeah, and then just make sure to. Oh yeah, you have your hazards. Okay, good. Great. Okay, good job. The aqueous. So for aqueous, that would be considered. Are you asking what is aqueous for this experiment, Anneli? Are you just asking in general what is aqueous? Okay, so the aqueous for this experiment would be considered the hydrochloric acid, the sodium hydroxide, water. But let me pull this lab manual up so I can make sure that we don't miss anything. And there is an ambiguous, let's see, cool, great. Yeah, so see how she has the listing of the specific sizes, that's great. And then right here, the waste, that's awesome too, good. Okay, great. Thank you. And then, yeah, the instrument balance scale. Just make sure that, like from the previous ones, at the very start, people were having a little issue between apparatus and instruments. Just remember, the instruments are the machines, and the apparatus is all of the glassware and stuff that we use. Yeah, okay, so you can go ahead and do it, Pedro, now. If you have either the paper or if you have Microsoft Word, you just have to go to share screen and then click the screen for it. Okay. Great. Oh yeah, and this is the polarimetry pre-lab. You may have done the pre-lab for you may have misread that the lab for this week was the acid, because I know it's a little confusing, but if you go to the modules, it'll show you on the schedule which one we're on for this week. So this week we'll be doing separation of acids and bases. And I did get your email, Pedro, so I understand the situation. Don't worry about having to describe further, what's going on. But yeah, this week we're going to be doing the separation of acids and bases. So go ahead and work on the polarimetry on the side, and we'll get you caught up with all the other stuff. You can contact me separately about all the other stuff, so that way we're not, going forward with Zoom about that. But this week we'll be working on the separation of acids and bases, just so everyone's on the same page. And that's the lab manual we're going to be reviewing. if you need to review any of the other previous labs, they're posted on my YouTube channel, and I'll make sure to send everyone the link again after class when I upload all of the video. So yes, yeah, go ahead, Adriana. Great, yeah, okay, yeah, and see, so if you list vacuum filtration like that, scroll back a little, yeah. So if you list it like that, this is how I want it to see it, because the thing is, some people in the first labs, they were placing something like, they just say vacuum filtration setup, and that is correct in the sense that that is what is going to be utilized. However, what would you use? How would you walk into a lab and say vacuum filtration setup? Well, you need your filtration flask, you need the clamp to secure it, you need the hose, and then you need the funnel. So yeah, great job. And then yes, those are correct waste. And yeah, so you can always look up online to see which sort of waste that all of these materials are. And I will double check to make sure that everything listed here is everything we need. So, okay, great. You're good to go now, Adriana. So we will switch back now, and I will go forward to address the lab manual. And one moment. The melting point. Okay, so that is one thing in the data that I will address towards the melting point at the end of class. And I'm gonna cover it in the lab manual, but the data that is provided, because I'm assuming you've already seen the data, Natalia, is does not give us the actual melting point data. So let me address that when we come to the data point, so that way that everyone's on the same page. Oh yeah, and the pre-lab calculations, we don't need to worry about that this week. In a theoretical situation, pre-lab calculation, the only thing that you would do for a pre-lab calculation would be to write down the amounts that you'd be weighing in order to perform your acid-base extraction. So understanding your crude inputs, and then your percent recovery, of course, will be calculated at the end. But in the section for pre-lab calculations for this week, everyone can place no pre-lab calculations were required for this experiment, and we'll be good to go for that one. No, I did not call your name, Liz. You're good. So within the procedure, I would say to utilize everything that is within here. So whenever you write your procedure, just make it from your lab manual in your own words. And then if there's no data present in the data section, you can either just like not put the data in that's required, or you can write there was no data regarding melting point, because that's what's going to happen later on this. But let me focus firstly on this, and then we will address anything further at the end of this, because I know that we have a lot of people who are waiting around to get into the intriguing topic of separation of organic compounds by acid-base extraction techniques. So this is a great way to separate compounds in the lab when you have a mixture of components within an organic system, and you want to separate it by utilizing aqueous, an aqueous solution, because as you know, organic and aqueous are immiscible, such as like oil and water. So they create two phases. And I really wish that I could show you in person. So I will really recommend everyone to watch the YouTube videos that are in the module, so that you'll be able to visually see this. So going forward, this is an overview of ideas that we've already covered within our class: recrystallization, chromatography. And as you will see here, this method involves partitioning of compounds between two immiscible phases. So the one phase, the aqueous phase, and the other phase, the organic phase. And that's why it's important within the lab to understand the two types of waste, because once the safety personnel have to come in and collect the carboys to properly dispose of them, we don't want to have some sort of precipitate on the top of our waste, and then the safety personnel potentially be put into danger, or them try to neutralize the waste and then them be put in harm's way. So we always want to make sure that we properly dispose of all of our contents correctly, especially when you think of the idea of the two immiscible phases. And so as we knew from the TLC and column week, we knew that adsorption was used in chromatography by utilizing our polar silica gel to absorb or adsorb our compounds, and then we slowly used our solvent to elute them, and they were separated by polarity. But in this case, we're going to be separating things by acidity or basicity. And so extraction involves selectively removing one or more components of a solid, liquid, or gaseous mixture into a separate phase, such as where we will be doing liquid-liquid extraction. And this is a very common method for removing an organic compound from a mixture. So if you have a mixture of compounds within a solvent, let's say dichloromethane was one that you guys used in TLC. So dichloromethane can hold a various amount of organic compounds, and you wanted to pull out something that's basic from it. So we'll learn going forward how we would pull out something that's basic and how we can pull out something that's acidic from our organic phase. So we need to remember these principles as our tried and true method of extraction. Firstly, the extracting solvent must not react in a chemically irreversible way with the components of the mixture. So if we remember back from our TLC lab where we had the post-lab question regarding the silica gel being acidic and what happens if you had an acidic compound on there, and they would be reactive. So if it reacts with it in a chemically irreversible way, decomposing it, it's like when you burn food in the kitchen. Once it's burned, it's burned. There's no recovering it. It's basically decomposed of, and it becomes a waste at that point. So we want to make sure that the solvent is effectively in equilibrium, that it is not reactive with it, and that it is inert is another word that we like to use in chemistry. Secondly, the extracting solvent must be immiscible, or nearly so, with the original solution. So once again, the aqueous phase and the organic phase. And so that will be the two sort of solvents that we'll be using, because solvent can be for water, or it also can be for organic solvents. Thirdly, the extracting solvent must selectively remove the desired component from the solution being extracted. And this part is from Gen Chem, that the partition coefficient K of the component being removed must be high, while the partition coefficients of all of the components should be low. So if you remember the partition coefficient, it's related to the concentration of a given compound. So when they say it's high, that means that the partition coefficient being removed is high within the extracting solvent, meaning that very large amount of the compound will be pulled into the extracting solvent, and then the rest will have a very low partition coefficient, meaning that it will not be able to be soluble within the extracting solvent. So that extracting solvent will pull out what we want and leave everything that we don't want to be extracted. Fourthly, the extracting solvent should be readily separable from the solute. Use of a volatile solvent facilitates its removal by simple distillation, which we will discuss in future labs. So this was part of the simple distillation. You remember how we had cyclohexane, like a crude mixture of it, and then you boil off your cyclohexane, it distills off, and you get your pure cyclohexane. Well, within lab, we utilize a system called a rotary evaporator. And what we do is we can connect, if you have a compound dissolved into a solvent, then you can actually go forward and put it on a rotary evaporator. It will distill off all of your solvent and then leave you with your pure compound there. So this is the idea, is that we want to make sure that we use extracting solvents that are very volatile. Some compounds that are not so volatile are something like dimethyl sulfoxide, DMSO, at the boiling point is in the 200s, I believe, like 200 degrees Celsius. And so if you think about that, that is extremely, extremely high temperature, very hard to remove, even harder than water to remove from a system, and let alone that it can decompose your compound if you're trying to remove it. So utilizing a volatile solvent assists you further whenever you want to actually extract your compound from the solvent. So going forward, we'll go ahead and go down here into the main concept that we're going to be focused on, and that is acid-base extraction. So we will be understanding the idea that most organic carboxylic acids, and now that y'all are in OChem, you probably have seen this before. A carboxylic acid, the carboxylate group right here, is a carbonyl group with an oxygen and a hydrogen. You'll always know that it's this carbonyl. It's a carbon double bonded to an oxygen with an alpha oxygen as well. And in this case, it's also an alpha carbon connected into the benzoic, the benzene ring. So it's benzoic acid in this case. So most organic carboxylic acids are insoluble or only slightly soluble in water, meaning that if you have like a very large amount of water, yeah, you're going to get a little bit of your benzoic acid dissolved into there. However, the benzene group, as you think about the van der Waals forces, that it's going to be extremely nonpolar, very hydrophobic. It really doesn't want to dissolve. However, if we use dilute aqueous sodium hydroxide, what we can do is actually deprotonate the acid by the base, producing the sodium carboxylate salt. So sodium benzoate is produced whenever you utilize sodium hydroxide with benzoic acid, creating a water-soluble solution alongside with your H2O as usual. So what we can see here is that, once again, benzoic acid is insoluble in water, but it's highly soluble in organic solutions, such as dichloromethane, for instance. However, if you were to take in your two-phase separation, your solution that contains your benzoic acid in dichloromethane in your separatory funnel, then you add in a certain amount of your sodium hydroxide water solution. You have two phases, remember, dichloromethane, organic phase, water, sodium hydroxide, aqueous phase. And then you were to take your separatory funnel, close it, shake it. What happens is that the benzoic acid is then deprotonated and turns into sodium benzoate. And that is soluble in aqueous conditions, meaning it would pull out of the dichloromethane. You can take off your dichloromethane. You're left with the aqueous solution containing sodium benzoate in the aqueous solution. So in this fashion, you can understand how important it would be for one to utilize this in lab, because then you can start pulling out things that you don't want. Or if you run a reaction and you want to get, product C, and you have, reactant A still left in your mixture. Well, if reactant A is benzoic acid, then you do it with a little sodium hydroxide wash onto it, and then you'll pull off your benzoic acid, and then you're left here with your dichloromethane with your organic compound, and then you're good to go. So that's why this is a really great tool within a chemistry lab and in research in general. Going forward, the really interesting part here is that if you wanted to reclaim your benzoic acid, then you can go ahead and take your sodium benzoate and you can reprotonate it by changing the pH back to acidic, or in the case of if you had an aqueous solution, you would chill it on the ice bath like that we're going to talk about later, and then you would add hydrochloric acid until it is acidic. And think of the pH scale, 1 to 14, 1 up to 7 being acidic, 7 to 14 being basic. You would reduce the pH down to where it's below 7, and then effectively you would finally precipitate out the benzoic acid from the aqueous mixture, and it would form on top as a precipitate, and then you would have a byproduct of sodium chloride as well, which is just a common byproduct when you're reacting sodium hydroxide and hydrochloric acid. So we'll notice that firstly, you can utilize sodium hydroxide in order to deprotonate your benzoic acid, creating sodium benzoate, which is water soluble. You can take your aqueous layer here and separate it, put it onto an ice bath, cool it down, then add hydrochloric acid, reprotonate it, and it will precipitate out because it'll become insoluble once again because it's back into its organic acid form, not its sodium benzoate ionic water soluble form under acidic conditions. So now we want to think about another thing, like when I was talking about at the beginning of the class, if we have a base and we wanted to try to get that to dissolve in, if we have an organic base, that's what they call it, because just saying the word base means that it could just be a salt like sodium hydroxide. In this case, we have an organic base, which is an amine in the system that we're discussing today. So the addition of hydrochloric acid to an amine, in this case, produces the corresponding ammonium salt, which is soluble in water, but not an organic solvent. So I wish the image was up here, but it's basically the reverse of the benzoic acid system. So 3-nitroaniline, focus mainly on the amine. I know that as you look at more of these structures, it gets more daunting because you see more and more chemicals added and you're like, oh my gosh, Scott, this is so confusing, what's going on? Ignore the nitro group. Even if this was aniline, I utilize aniline in my lab all the time. It's great. And you can just cover up this NO2 group, does not matter. What matters is this amine because it is an organic base. So this amine, the electrons come over here and then they remove the proton from hydrochloric acid, creating the protonated 3-nitroaniline, which is the ammonium salt. These are called ammonium salts. So amines can react with acids in order to create ammonium salts that are water soluble. So it is the reverse of the other situation there, Whereas if you react the benzoic acid with a base, you can create the sodium benzoate. In this case, you can react an amine with an acid and create the ammonium salt. So as you can see, there's the two different systems, and you kind of see where we're headed now, because obviously if you do one, you'll get a specific one and it won't affect the other, and then vice versa, then you'll get the other as well. So going forward with, you have now your ammonium salt and it's water soluble, you have it in your acidic aqueous solution, right? What you can do is the exact same thing that you did with your sodium benzoate that was in aqueous solution. You put your hydrochloric acid with your ammonium salt solution on ice. You slowly add in your sodium hydroxide until it becomes basic. And then finally, it deprotonates your ammonium salt and turns back into 3-nitroaniline, which will precipitate up out of the aqueous layer, because once again, 3-nitroaniline, not soluble in water under basic conditions. So just mainly understand the differences between that benzoic acid, or more to say organic acids, when reacted with a basic solution, will become soluble and create the sodium ion of that organic acid. And then on the other hand, if you have yourself an organic base, such as an amine, that it can react with an acid in order to become water soluble, and it becomes the, well, in the case of the amine, it becomes the ammonium salt. So going forward, you can see here, we have our three conditions that we would be utilizing in lab. We would have benzoic acid, 3-nitroaniline, and naphthalene. So the big thing here to notice, on the naphthalene, we don't have an organic acid. We don't have an organic base. So what do we have? Just organic. So what happens if we react it with an acid or a base? Nothing. So that's the important thing to see here, is that if you had something like that in a reaction inside your lab, then you could go forward and separate out these materials and be left with that, as well as having your materials on the side. So going forward, we'd be separating a mixture containing benzoic acid, 3-nitroaniline, and naphthalene. Calculate the percent recovery of each component in the mixture after you've gone forward and recovered it, and then measuring the melting temperature of each isolated compound. So yeah, it looks like here that we have the sizing of all of our glassware, and go ahead and make sure that you just utilize the sizes that they're talking here for your apparatus section. Just make sure to utilize all of the different sizes of glassware they use here. Make sure to add in diethyl ether will be one of the hazards. Right here, your three things: benzoic acid, 3-nitroaniline, and naphthalene. Those three are going to be hazards. Of course, we said diethyl ether, and then aqueous hazards, hydrochloric acid, another aqueous hazard, sodium hydroxide. And let me see if there's any other here just to help y'all out. So you can put in the machine section for near melt station, you can put in the machine section the scale. However, I noticed on the data, and we'll review this after we go through the flow chart, just to kind of hit home the point that there is no melting point. But go ahead and perform your post-lab questions as usual here. Understand what's going on, figure out all of these. And finally here, this is going to be exactly what we'd be doing, right? So you have your solution, okay? You have your 3-nitroaniline, you have your benzoic acid, you have your naphthalene, all dissolved in diethyl ether, your organic solvent, right? Placed into your separatory funnel. It was like the funnel shaped thing that we looked at within the module. Then, firstly, we're gonna add 15 milliliters of hydrochloric acid and extract it 3 times. So what happens? The aniline, the organic base, turns into the ammonium salt, which is soluble in aqueous conditions because it's acidic, it's become the salt, and it's salted into the system. So you have your aqueous extract here. Then you have that on the side, and you remove that flask and you label it HCl extract, hydrochloric acid extract. Then you cool it on an ice bath. You finally neutralize it with 4.5 molar sodium hydroxide, same molarity. Just makes it easier to understand the quantity. In this case, if it's 3 times, then you would neutralize it with 3 times 15, so 45 milliliters of 4.5 molar sodium hydroxide. Your 3-nitroaniline precipitates out. You perform vacuum filtration because you have a solid since it's precipitated out. performing vacuum filtration, get rid of all of the water. Then you dry it in the oven, and then you'd find your percent recovery and melting point. So you still have your organic layer though sitting here, and what do you have left? You have your naphthalene. You have your benzoic acid still in the system because acid does not pull out organic acids, only base does. So what do? We return to the separatory funnel for the extraction, and we start performing we start making our solution basic. So we take our 15 milliliters of aqueous base, 4.5 molar sodium hydroxide, and then we extract it 3 times, pulling out the sodium benzoate every time. So the organic layer, they just discard it. Not really sure what happened there. However, your organic layer would be the naphthalene, right? Your aqueous layer in this case, the sodium hydroxide extract, would be the benzoic acid. Or, well, it would be actually, sorry, the sodium benzoate because it's dissolved in here and is deprotonated into its sodium benzoate form. So you have your sodium benzoate here in your sodium hydroxide extract. You cool it in your ice bath. Once again, you neutralize it with your hydrochloric acid, and benzoic acid comes back out of your solution. You vacuum filtrate it, pull off your aqueous, pull off the water, dry it out, put it in the oven, completely dry it, find your percent recovery and melting point. So that's the flow chart to show exactly how our experiment would be performed today. Finally, I'm going to go forward to show everyone the data here. Go back. All right. So students should use the following data table to complete the procedure using the following data table based on your the first letter in your first name. So make sure to complete your post-lab questions, of course. If you're A, C, or E, of course, everyone can read here, so just make sure to see if your first name starts with the letter of the alphabet from any of these letters here. It'll be which data that you use. As usual, everyone's doing great on that. I haven't seen any people mess up on that so far. But as you can see here, unfortunately, it looks like that there is no melting points given. So with regard to people who were asking about that, you can either write the melting point was not found in this experiment, the data did not give us the melting point, and just go forward with it. And we'll just go ahead and say that you know, it would be like if we ran out of time in the lab and we didn't perform the melting point. But it would be good as a practice for us to do it, because not only would you see visually whenever you reacidify or rebasify your organic compound, but also that you can take it and go put it in the melting point and confirm with yourself that, oh yeah, the melting point for this is exactly correct. So for the instance of, let's see really quick. So for benzoic acid melting point, 122 degrees Celsius versus 3-nitroaniline. So 122 degrees Celsius for benzoic acid, whereas 3-nitroaniline is 114. So that's about 10 degrees difference. And you would definitely notice that in the melting point machine if you had pure compound. So yeah, at this point, it looks like that we've covered everything for today. So I'll go ahead and close off our video for the people who are watching it on YouTube.